Hello and Assalamualaikum everyone. I'm from Group 1 and this is my team member Rafael MA22127, Kohiliang MA22124, Muhammad Syafiq bin Khalid MA22118, Muhammad Irfan bin Johari MA22120. So today I would like to present about our project. The title of the project is Study of Cavitation in Hydro-turbine. So for the introduction, what is turbine? Basically, turbine is one of the mechanism that generating electricity by harnessing the force of moving water and converting it into the necessary spinning motion to power the generator. Turbine achieve this either through mechanical gearing or electromagnetic induction to produce electricity. Next, the objective of our research. The first one is ascertain how the system's stability was impacted by the particle and wear of the blades. Gain information of how the cavitation impact to the overall turbine. The third one is know the causes of the cavitation and how to prevent it from happen. And the last one is the focus on how to solve the problem of Chilla hydroelectric plant. Next, how did the cavitation happen? The cavitation happened from the prime culprits for damage to Kaplan type, which is the type. The first one is fatigue, second one is erosion from silt, and the last one is cavitation. Cavitation also happen with the presence of hard particles like quartz and feldspar cause cavitation. It will lead to tip clearance cavitation and tip vortex cavitation. Next, the importance of the study. The first one is to identify several variables such as velocity, mass, concentration of abrasive particles in a liquid flow, grain size, and particle collision angle impact on the turbine blade surface. Second one is effectiveness of the progression of the sediment while processed in turbine blades. The third one is to learn on the method that can prevent from the cavitation happen, not just for Kaplan turbine and also for other type of turbine. And the last one is to help us to gain more knowledge on the turbine that did not written in syllabus and learn on how to do research.
Assalamualaikum. My name is Muhammad Irfan bin Hijrani and my matrix number is MA22120. So I will explain more about our project. Okay, we start with our type of turbine. So there are two types of turbine. The first one is impulse turbine. The individual jets of fluid striking the bucket and generate the torque, and then the change of velocity of a water jet into energy. So there will be no pressure drop across impulse turbine. Another type of turbine is reaction turbine. Reaction turbine derive power from pressure drop across the turbine. It also changes pressure as water move through the turbine and give up its energy. Usually, reaction turbine totally immersed in water and angular and linear motion convert to shaft power. So there are three types of impulse turbine. The first one is Pelton turbine, cross flow turbine, and turbo turbine. For reaction turbine, there are two types of turbine, which is Kaplan turbine and also Francis turbine. So as we can see, these are the example of turbo turbine, cross flow turbine, and also the Pelton turbine. And these are the example for Kaplan turbine and also Francis turbine. Next, we move to type of cavitation in hydro turbine. So, what is cavitation in hydro-turbine? Cavitation is a physical phenomena that happen in flowing liquids when the local static pressure drops below the vapor pressure of the liquid and cause formation of vapor bubbles. So, the first type of cavitation is traveling bubble type cavitation. It happens due to the pressure drops in a fluid flow and then it travels along the surface of an object exposed to the flow. So this movement is typically induced by the shear force exerted by the fluid as it flows past to the surface. So the second type of cavitation is leading edge hub cavitation. Leading edge hub cavitation is a type of cavitation that occurs near the hub and particularly at the leading edge. So the pressure gradient can be relatively high at the hub or the plate. So as we know, when the pressure is high, so the velocity will be low. So this occurs because the fluid flow experience compression and also acceleration as it enters the narrow gap between the blade root and also the hub. So the third type of cavitation is tip type clearance cavitation. Tip clearance cavitation is a type of cavitation that occur in turbine, compressor, and other rotating machinery because of the clearance between the rotating blades and the surrounding casing. It happens when the fluid flow through the rotating blade. It encountered a sudden expansion of the flow passage due to the clearance. So this expansion causes a drop in pressure, leading to the formation of vapor bubbles. Then the vapor bubbles form at the blade tips where the pressure drops. So the last type of cavitation is the tip vortex cavitation. Tip vortex cavitation is a specific type of cavitation that occurs at the tip of the rotating blades, usually in the propeller. So when a blade or propeller rotates through a fluid, it creates a swirling motion due to the pressure difference between the pressure side and the suction side of the blade. So the rotation of the fluid at the blade tip can create a low pressure zone in the core of the vortex. So if the pressure drops below the vapor pressure of the liquid, vapor bubbles can form within the fluid. Next. So these are the example of tip clearance cavitation and tip vortex cavitation. I think that's all for me. Thank you.
Hello and good day to everyone. My name is William. ID number is MA22124. Today I will talk about the case study of our project, which is the cavitation of the hydro turbine and the prevention of the cavitation. So first, our study area is the Chila hydroelectric plant. This hydroelectric plant is located in the India. It is a run-of-river system on the Ganga River situated in Himalayan foothills, with the design height of 32.5 meter and a speed of 187.5 rpm. There are four 36 megawatt Kaplan vertical shaft turbine. So today our focus will be on the Kaplan vertical shaft turbine. So what is the problem? First, the turbine blades have severe erosion. It is also have the cracking on the trailing side. Runner chamber show deterioration. Drainage pump impedance damage and the energy extracted too low from the specification. This all effect is come from the cavitation. So now we will see the factor of the case. So the Kaplan turbine blades have scratch. So we recognize it as the tip clearance cavitation. So what is the factors? The clearance size between stator and rotor. The pressure differences also because when the velocity of the water become very high, the pressure will drop and the pressure will become below the saturated vapor pressure, then the cavitation can be happen. After that, there is also a jet water critter, which is it leave the suction side of the blade runner, which also can cause the cavitation. Kaplan turbine blade scratch. This is caused by the traveling bubble cavitation. First factor is the water density and viscosity low, which is can create the bubbles. Since the Ganga River have a low density and the viscosity is very low, there are very bubbles created in the turbine. The velocity of the Ganga River is 30 km per hour. So when there is a high velocity, low pressure, so when the pressure is become lower than vapor pressure, it will create the traveling bubbles. The weather also is the factor because when there is a bad weather, which is raining, river flow will increase. So same as the before, when the river flow increase, velocity also increase, then the pressure will low. And the rapid change in pressure also created bubbles. Sometimes rain and sometimes doesn't rain. Since the hydroelectric is located at the downhill of the Himalaya, so the pressure and the weather always change. So sometimes it's raining, sometimes it's hot. So the pressure difference create the bubbles. Now the third is Kaplan turbine blades have scratches. It is because of the hydro-abrasive particle. This is because the river has many small sediment particles, and when the particles crash the turbine blades, it will create the impact zone. So what will happen? So hydro-abrasive can cause the cavitation because when there is an impact, there will be crack, and this crack also can be counted as a cavitation. So when damage surface, and it can also increase gap size. So when the gap size increases, it will have a higher leakage. So when all of this happen, it can bring to the less availability and lower efficiency, which is less energy production. It's also related to our problem statement, which is the power extract from the turbine is lower than the specification. The fourth factor is Kaplan turbine blade scratches, which is hydro erosion. So this can happen because the small particles have many type of cracking. So the first one is low impact angle, but in the high speed. Let's say that I have this surface and there's a stone. So when a stone with a high speed come, so it will scratch the surface, right? It will just like, it will pull and it will create a high friction. Second is low speed, but high angle. So when the high angle happen, come high angle of the sediment, it will crash. So when it crash, it will create a crack because the angle is higher, so the pressure is higher. And the third one is flake formation due to the high impact angle and medium speed for ductile material. Flake formation due is just like impact of the meteor. Let's say this is Earth and the meteor come with many flake. So it will also can create the crack and the good impact which can damage our turbine blade. And the last one is the brittle fracture at high impact angle, which is also can cause to the brittle material because some of the turbine blade was built with the brittle material, so it's easy to be cracked. So it will create the cavitation.
Hey everyone, my name is Professor E, and this number is M82127. Now I will talk about the effect of the cavitation to the turbine. The first effect that caused by the cavitation is the erosion and material loss in the turbine. As we know, cavitation is the formation and collapse of bubbles that subjects the metal surface of rudder blade and draft tubes to high frequency cavity formation and intense pressure. The process is repetitive, occurring thousands of times per second, leads to pitting on the metal surface and impose significant stress on the material, causing the material to fail due to fatigue and corrosion. The phenomenon also happens on the low pressure side of the turbine runner blades. The corrosion in the runner surface can result in pitting depths of more than 40 millimeters and material losses up to 200 kilograms for several years. The erosion potential of collapsing bubbles varies and produces different results. The affected area may initially have a frosted surface with visible pipes becoming more permanent over time, which is shown in the figure. The erosive effects of bubble collapse vary, resulting in varying degrees of damage to turbines. The next effect caused by the cavitation is the hydraulic efficiency reduction. When vapor bubbles form and collapse, strong localized forces are generated on the turbine surface, resulting in material corrosion on the runner surface. This erosion increases surface roughness and producing heating, which creates an irregular forms that interrupt the smooth flow of water through the turbine. These flow interruptions are then worsened by blade angular deformation. leading to forced separation and a reduction in energy conversion efficiency. The collapse of bevel particles near the solid surface also generates shock waves and liquid jets that create disturbance and lead to local pressure fluctuations and turbulence. When the bubbles in port is closing, the turbine efficiency drops from 5% to 10%. The loss in efficiency also causes frictional losses to increase, turbulence levels to change, and operating costs to increase due to the of requirement for regular maintenance and replace. Okay. The next effects that cause by the cavitation is the excessive vibration and noise. This is the major impact that caused by the cavitation. As explained before, during the cavitation, the bubble will form and collapse, causing a shock wave, pressure forces, and impact forces in the field, generating several mechanical vibrations. This vibration, along with the liquid jet's impact and flow disturbance, then will lead to the dynamic and unstable system behavior. The resulting noise is often tonal and can travel through the field, resulting in undesirable acoustics in the surrounding environment. Furthermore, pressure fluctuations may align with the system components with natural frequencies, creating resonance and modifying vibration and noise levels. Then, this combined of resonance and unstable cavitation forces can affect the system stability, leading to operational challenge and potential long-term damage. Okay. I will talk about the cavitation prevention and mitigation technique. The first method to prevent cavitation is the air injection method. This effective method helps to prevent cavitation during turbine operation. The operation of the turbine under different conditions such as hard load, full load, and overload can lead to an increase in dynamic instability due to cavitating field force, then resulting in pressure fluctuations and power oscillations. However, these fluctuations can be reduced by injecting air under the runner blades during turbine operations. In this measure, pressurized pressurized air is injected into the horizontal plane of the runner center line at the discharge. The air flow through all the tubes is integrated into each injection point with constant pressure and constant discharge. This technique has been shown to significantly reduce pressure force amplitudes under both hard load and full load operating conditions. As what we found in the research, this method has resulted in an almost two-fold decrease in the rate of pressure fluctuations in the various regions of the hydraulic turbines. This technique has also been used on the Kaplan turbine model to mitigate the deep leakage cavitations and reduce vibration levels. In this design, evenly spaced holes on a stainless steel manifold are carefully positioned as shown in the figure, directing pressurized air just above the center line of the runner blade to ensure a comprehensive assessment of the turbine performance. Various monitoring instruments, including an accelerometer, high-speed flow, visualization tools, lightning setup, and a data acquisition system are employed for enhanced observation and measurement. Despite the success in reducing vibration levels, this inject air injection method comes with a trade-off. The injection of air into the flow path can result in a loss of turbine efficiency. The efficiency is primarily attributed to the additional energy required for an injection and its interaction with the water flow. The next method is the design improvement of turbine space and blade profile. The optimization of the turbine space and the design improvement of the runner blade profile play critical roles in enhancing turbine performance. The run, being a vital component, significantly influences efficiency and serve as a key factor in preventing cavitation. To achieve optimal results, uh, an analysis of pressure and velocity distribution is conducted. This analysis takes into account various factors including blade curvature, thickness, hydrofoil arrangements, angle of incidence, and blade dimensions. Enlarging the turbine area and optimize the runner blade design is a crucial measures, particularly in preventing cavitation under non-standard conditions. The key considerations in the process involve the curving of blade edge at the inlet and outlet, the distribution of force angles, and the shape of the runner blade to mitigate extremely low pressures during operation. Additionally, maintaining appropriate guide bend angles is vital for ensuring uniform force distribution and promoting stable rotation. In essence, this design improvement contributes significantly to the prevention of cavitation and the overall optimization of turbine performance. Next, to reduce cavitation and overcome change in turbine performance characteristics, it is also crucial to set the turbine at an appropriate height above the water level when installing it. The elevating of the suction head leads to a reduction in the absolute pressure at the outlet of the runner. Due to reduced water level, this becomes even more important during part load operation. According to the trauma cavitation coefficient equation, on the sigma, which is the cavitation factor, will increase as the suction head decreases, allowing the turbine to operate in the self-operation operating zone. For popular turbines and turbines, this for popular turbine, these kinds of high specific speed turbines, for the high specific speed turbines such as popular turbines, the runner outlet speed is very high, resulting in a reduction in the runner outlet pressure and increasing the risk of cavitation. Thus, the suction height is critical in mitigating the risk of cavitation. The main objective is to find a suitable setting level for the hydroturbine turbine to reduce change in efficiency and cavitation erosions. Okay, that's all for me. Thank you.
Now, for the third way of prevention, we will use cathodic protection. There are two types of the cathodic protection. The first type is galvanic cathodic protection. It uses highly reactive metal linked through a conductive medium, and the anodic material will corrode and sacrifice itself. The example of the material is zinc, aluminium, and magnesium. As we can see in the figure, there are two parts of the steel. The left side is cathode and the right side is the anode. So the anode will sacrifice itself and it will save the cathode from the electrolyte that will bring to the erosion. Now, for the second type, which is the current cathodic protection. The cathodic protection will use external power to provide continuous current, and the continuous current will flow through the material, and the current will oppose the natural corrosion. So usually, if the galvanic fail, the current will be used, and it will bring to the success protection. Now for the fifth, which is the surface coating. So how the surface coating work? The surface coating can work as it can reduce impact by hard coatings. The hard coatings material usually from alloys, paints, and ceramic paste. And also, the most used is the tungsten carbide-based composite. As the researchers say, most essential qualities are strong bond to the substance. Therefore, mostly the analytical and experimental methods will be tested first before they will start the surface coating. So the last one is the cavitation erosion resistant material. So as we can see in the figure, there is a super hard particle coming to crash the material, but the particle will meet destruction or it will be bounced back to the other place. Also, we also will not focus so on the super hard material because the other material such as the high elasticity also can save the material from the erosion. So let's talk on the erosion resistant material. So the top choice is the austenitic stainless steel because it is very cost effective. Austenitic stainless steel also have a high elongation, high tensile strength, high impact resistance, and also high yield point. It because it containing 13% chromium range supreme, which is best for the fighting cavitation. It also can boost impressive resistance and easy weldability. So for the erosion resistant material, it is better if we can weld back the damaged part because the more we welding, the more resistant it will become. So that's all from me. Thank you.
Then about the performance equation that relate to the cavitation. Okay. To identify the cavitation occurrence region in turbine, Professor David Thoma has proposed a dimensional number which is called Thoma cavitation factor, and sigma is the symbol. This is the equation to find the value of the sigma, where this is Hp minus Hs over H. Hb is the barometric pressure head, while Hs is the suction pressure at the outlet of the reaction turbine. H is the net head of the turbine. Hb is also can be derived as an atmospheric pressure head minus vapor pressure head. To indicate whether there is a cavitation occur in the turbine, we have to we have to compare the value of the cavitation factor with the critical cavitation factor. If the value of the cavitation factor is higher than the critical cavitation factor, then the cavitation will not occur. However, if the value of the cavitation factor is lower than the critical cavitation factor, then the cavitation will occur. To find the cavitation, we have to use the empirical relationship. Here are the different equations that used to find the critical cavitation factor for the different reaction turbines. For Francis turbine, the critical cavitation factor is found by using this formula. Now for popular turbine, the critical cavitation factor is found by using this equation. And the NF is NF is equal to the specific speed of the turbine. Okay, that's all for me.
Lastly, I will conclude our presentation with the conclusion. So for the conclusion, we learned what is cavitation is. So cavitation is a phenomenon where surfaces are exposed to high local stresses and high pressure. The second one is in hydraulic turbines, cavitation is impossible to prevent but can be minimized to a level that is acceptable. The third one is in hydraulic turbines, cavitation is impossible to prevent but can be minimized to a level that is acceptable. Last one is the design of the turbine components. Most of the time, the improvements were not that possible. And I think that's all from us. Thank